Cool. So we are live, even if it's, according to my clock, 2 minutes left. Let's do a sound check. And, 1 2 1 2 testing. So let's see if you can hear me. Really awesome. So we're going to start in like a minute or so. Okay, so welcome to software testing. This is lecture number 5 or so, and we are gonna talk about test effort assessment. And basically, how do we know that the testers or we are doing a good job and or not doing a good job? How do we know stuff about what we did? How can we, put a number on what we did, really, on how good we were in doing what we did? So I think maybe you have seen the requirements pyramid before. In the top of the pyramid, there are 2 clouds. This is the needs, and they are clouds because they are not really defined to begin with. They are ideas in the head of people, or needs perhaps in the head of people. So I'm just going to do it like that. And so these could be that we need to be able to store information, for instance, in a web application, and they need to store information in order to retrieve that information later. So let's say this is a blog. So we're storing blog posts, and that is sort of the need is really, I need to share my thoughts with the world. So that could be one of the clouds, right? So and sharing your thoughts or writing down your thoughts could be implemented in so many different ways. It could be implemented in so many different requirements itself. We could define that in so many weird ways. Like we could have manual things that implements these. So I'm, talking to someone, secretary, who writes down my thoughts. And then, we could have a long list of things that could happen. It could also be that I realize this need through a computer program. And when I do that, I sort of decide a lot of different things. So I say that, I need a web application with an editor where I can edit the text and I can set a title and stuff like that. And then we're approaching the feature thing, right? So let's say that we can create and edit and perhaps delete texts or blog posts. Now we are stepping down into the features. I also want to be the only one doing this. I don't want anyone else to be able to post thoughts in my name, right? So in my blog, I want to be the only one that can log in and do this. So the need to be the only one is realized through a feature that could be an authentication system. And perhaps the authentication system is then realized through a number of requirements. And the number of requirements could be to be able to log in. But if we're going to, have a blog system that many can use, perhaps we also need to be able to register people, or we have an administration to be able to administration software to be able to handle users or something, stuff like that. So these needs can be realized, or more well defined through requirements or features, and then we define those features as requirements. That is more or less the exact ways of writing them down that you learn, and you've seen use cases. Perhaps you've seen lists of features. And lists of features are often less defined than an actual requirement, and that use cases can also be in different stages of definition, right? So we can have these really brief ones that someone wants to do something. But then we can have these very well-defined ones where someone logs in, but if this doesn't go well, then we have an alternate scenario for that, and we define all that. So I have one of those to the left here. A user wants to get access to a restricted system. User wants to get access to a restricted language. User requests access, system asks for credential. User gives credential, system verifies credentials and presents restricted access. So there are a number of different things here. One is that, this has nothing to do with buttons, with user interfaces. This could be a console application, this could be a web application, this could be a phone application, whatever. We are not talking about passwords, we're not talking about usernames or anything, right? We used a more abstract way of defining these credentials. So a credential could be an image of my face, which is authenticated through the phone cam, right? So system asking for credentials could also be interpreted. It could be show your face. It could be enter username and password here. It could be show your ID. Essentially, a requirement on this level could be implemented by people instead. So we have some people representing the system, like a guard in the door of a bar or a disco or something like that, and then the user, the one who wants to go in there, ask for access, and then the system or the guard ask for, okay, I want to see your ID if you're old enough for this. User gives credentials, system verifies credentials and present restricted access. Okay, but what I want to say that we have different levels of abstraction here, so the features are even more abstract. I see students writing use cases less abstract than this, but I would like you to think of this. Don't specify too much when you're writing use cases. This is not about requirements, this course, but when you see requirements, you might encounter requirements that are very specific, very close to the UI, and you can have other requirements that are very abstract. And there, when you receive something that is abstract, that gives the programmer freedom, so which I think is a good thing. So try to be abstract. That gives a programmer freedom to to implement this in their way, right? To interpret this. So you see on the left here, on this level, we had use cases. On the right, we had specifications. So not all requirements are defined in use cases. So some can be that we want to be able to, the system should be responsive. For instance, could be a non-functional requirement that are written in the specification, and it can be abstract as that. It could be that we don't want the user to be bored when they're using this. That is very abstract, right? Okay, and it could be very specified also. A login attempt should never take more than 1 second. So, but that restricts the programmer's effort in doing this. So the reason that I'm talking about this is that testers often receive requirements, and then from the requirements, they are defining the use of the system, or the limits of the system, right? So when we say that we interpret the specification that says that the system should be responsive, and then we create a test from that. and the test needs to be very specified. So when we move downwards in the requirement pyramid, down to the test cases, we are getting more and more and more specified. And I want your test to be specified. If they are too abstract, you won't be able to test anything useful. Okay, so a test for user response or system responsiveness could perhaps be that, okay, the system must respond within 1 second for this. And then we run the system and we take the time when it starts and take the time when it ends. And then we, assert that this was shorter than 1 second. Okay, so we move down in this. And from the use cases, we also get scenarios. And a scenario is a path through a use case. So, for instance, the main success scenario is when we actually are able to log in with correct credentials. We are let into the disco, right? But we also have an alternative here. User gives invalid credentials. System presents that credentials are invalid. And perhaps we should say something more. You're not allowed to enter, right? Something like that. So that is an alternative scenario. We're not let into the disco. We must find another ID card. Or like a friend of mine, just adjusting the numbers on it. So the scenarios for logging in, here are some that I found. First scenario perhaps is just to navigate to the login page. And suddenly we are very specific when we're talking about test cases. Now it's a page. Now there are buttons pressed. Now there are fields entered. So I usually, when I design scenarios, I usually start with all the failures and then do the main success scenario. Because when I have the main success scenario implemented or done, it's easy to say that, oh, I'm done. But really, there are often many scenarios, like fail login without any entered fields. So without a username and password, we cannot log in. Or without showing a face, you cannot log in. And then we have fail login with only username, so no password, fail login with only password. And as you see here now, since the tests are very specific, the implementations that do not follow these test cases, like the camera one, is now lost, right? That application that implements those scenarios would need to be removed or have different test cases. So test cases are specific, and try to make them that way also. Fail to log in with wrong password, or fail to log in with only password. And then I assume a correct password, but not writing the username. Because, I can imagine a bug where we only check the passwords and don't check that we'll both match username and passwords. Therefore, I have a test case for that. Fail to log in with wrong password, but existing username. Fail to log in with existing password, but wrong username. And you see that when I name these, I'm using actually the same thing that we talked about when we did naming for unit tests, sort of. We're talking about the input and output, but not specific in the name of this. The actual test case do contain specifics. I'm just going to go down to one of these, fail to log in with only password. So if you look at this one, I use another test case as input. It could be a prerequisite instead, but I want to specify that you should navigate to page again. Here you can see that you should not enter any password. You're entering this exact specific input, the password with big P, and let the username be empty. Yeah, and then you press the login button. So we're very close. And for all of these, it's like that. Yeah, and then finally 1.7 successful login with correct username and password. 1.8 still logged in after reload. It could be that we are getting a login message that, oh, you succeeded to log in, but we're not really logged in. So and then we can resend information. Yeah, web applications, it's you can resend information sometimes with F5, and double posts. You probably experienced this when using the web, where you posted a blog post, but you got two because when you reloaded the page, you accidentally posted it again. And we want to avoid that, so we have a specific case. 1.9 logged in another window to make sure that you're not doing anything stupid. Okay, so we have all these scenarios, we have all these test cases, we have a connection to one requirement. So in order to see if we have done all of these scenarios correctly or tested the requirement fully, we can create a matrix, so we can have requirements on one end and test cases on another end. And then we just make sure that each requirement has at least one test case. But as you did see, for this one, for one use case, the abstract use case, right? I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 scenario or test cases, one for each scenario. So, and actually, some scenarios, or failed login scenario, this alternative thing, I had several test cases for that one. I started with all of those. So, so if we want to make sure that, okay, we've covered all requirements, let's make a matrix and show that we've covered all requirements. The interesting thing here is that requirement 1 use case, I didn't write this one, so I'm actually not into the details. I don't know what 1.1 means here. It could be a scenario, I'm not sure. What that is scenarios, of course it is, because it's requirement 1 all the way here. So we have a lot of different scenarios, and then we have technical requirements here. And then we have test cases here. Usually I try to make sure that there is some standard here, deciding what these numbers mean. But in every project, we can decide what these numbers mean. So you decide something that is useful for you. For instance, when I name test cases, let's see if I can find those again. When I name test cases, I use a naming strategy so that, let's look at this again. So test case, the 1 here means use case 1. And this is just an index of the test case number. So the first test case number is 1, 2, 3, 4, and so on, right? And when I get down to, let's see, another requirement, which is the first one, the other use case, the log out use case, then I have another number here in the beginning. So this is the use case number, and then I have the test case number. So if you know that information, you can unlock what we call traceability. And traceability was one of the goals of testing also, right? Because if we change a requirement, we might need to change all the test cases connected to that requirement. If we remove a requirement, or we even remove a feature, we also want to remove perhaps all test cases belonging to that, perhaps all code connected to that. And we should not waste time on that, maintaining that code, running those tests anymore, because we don't have that requirement anymore. So traceability is a good thing. And this is called test traceability matrix because it traces test cases to requirements. Some requirements have more than one test case. We usually want to have at least one test case per requirement because we want to show that we've implemented this. We want to know if we implemented this. At least that we did something in that regard. Okay, so we've been working, so this was, requirements and use cases, but what about unit test suites and how to assess those? So I would say that when it comes to generating test cases, we have another lecture for that specific thing. So we're going to look a bit further into that and how to go through these things. And some part of that is also included here. So you're going to recognize things. But I want to go to unit test suite because you are working with that in your assignment for this Friday, the deadline for Friday, right? So how do you know if you did good or not? So let's take a look at test suite. This project, Yoda.org, Yoda Time. So this is a Java library, provides quality replacement for the Java date and time classes. The design allows for multiple calendar systems while still providing a simple API. So we have a default calendar, but we also have, all of these other kinds of calendars that are used by other people in other parts of the world. So if we have an internationalized app, this might be a good idea to use this thing instead of the standard library in Java. Okay, so this is no longer in active development, except to keep time zone data up to date. Sure. So the interesting thing here is we have a lot of code, a lot of classes, and the main time. So there are, a lot of classes here. Yeah. All of the abstract ones, all of the chronology classes, all of the converters from different things to different other formats. A lot of code, right? This is quite an old project also, so it has, evolved for a long time. So more and more code has been accumulated. So how do we know that the developers, how do we know that it works at all? Oh, yeah, did they test anything when they wrote this code? Yeah, they probably, at least ran the code. So if we search a little bit deeper, we can find that they have a home page. And then we can, read their documentation. We can, find out stuff about their work, right? And I found, in the end here, I found test results. So we can, look at their test. And this is a test report. This talks about how they tested their things. So we can see that different packages have different tests. So this one has 279 unit tests. This other one has 3,014 unit tests. So there are a lot of test cases here. We can see that for none of these, we have any errors, failures, or skipped. Skipped means that this test could not be run for some reasons. Perhaps we say to the test runner, we don't run these test suite because we don't have time for that, right? It could be failures, which means that we have an assert that did not, so the expected behavior didn't match the actual behavior, right? So that is a failure. And then we can have an error. And in this, there could be that Java is crashing while running the test case. So either the test case code itself caused the crash, or the code that it exercised, the system under test that it exercised, the class or the function or whatever, the part of the system that it exercised crashed, or through an exception that was not expected. So that is usually called an error. We can say all of these tests succeeded. We can see how long it took. Oh my God, it didn't take that long. So we have a slow one here. The chrono test, 172 of them takes 2 seconds or whatever this is. I actually don't know what it. I hope that it's not hours. I hope that it's seconds, because we talked about fast test suite, right? That it's important that it's fast. We can look into these, and we can look at the different classes. So in the field names, so we see that they have these classes and these classes and these classes. But yeah, this is good information, right? Because we're starting to think about, this format class, test date time formatter has 76 tests. That sounds trustworthy. I don't know. I have no idea, actually, how worthy that is. So would you trust this code with your life? Or would you, trust this code with your money from just looking at this report? So I also downloaded the thing, and then I ran it on my computer, and some of the test this could be different branches, right? So I just took the main branch, and then I ran it, and a number of test cases failed. I've not looked into it deeper than that, but I was just interested in looking at it. So the interesting thing is here that just knowing how many test cases there are for one class, for instance, doesn't say more than that class has test cases. If they fail, if the test cases fail, then we know that there is something wrong there. But even if they are 3,000 test cases, we don't know if there are bugs there. So can we go deeper or understand more of this? So let's talk about that. So really, you remember that we talked about correctness, and correct means that the implementation is correct. There is no input for which the system under test gives a failure. That means correctness, right? And then we had reliability, which was that if we have a random input in the input domain, which is all the input possible to this particular part of the program, what is the chance of getting a failure? And for most programs that are not toy programs, I mean like that only take one or two different inputs perhaps, and they are very small, like a Boolean input or something like that, then we can test everything. But as soon as it's, one integer as input or one letter or whatever, not one letter, we can handle that. But as soon as the input is getting a little bit more complex, it takes forever to test. So we need to reduce the number of test cases. That was the test selection problem, right? And we want to do that in order to find adequate tests, the good enoughs. So how do we solve the test selection problem adequately, or measures of good enough, right? So I want to give you sort of an idea on how I think about this. And I think this is reasonable to implement in the assignment 1. So I see that I get a question. I'm going to take that after this slide, I think. So what I think of, or when I think of a test, I think of that as a constraint on the solution space. So you remember the requirement pyramid, right? And we had abstract requirements in the top, and then we're getting more and more specified. And then I said that the test cases are even most specified because we're saying exact input and exact how to input these things. So solutions that have a different user interface does not match those test cases anymore. So we can remove all solutions that are not correct anymore. So I think of tests as constraints on a solution space. So just start to think about all code ever written and all code that could potentially be written. And let's place all of those in one cloud. It's a huge cloud, right? This is countable infinity, more or less. It's not actually an infinity because, there is limits for how long a program can be to be stored in a computer, but it's very large, right? So this includes more or less everything, all programs. We could, define some of these as, okay, some of these are all Java programs, or all programs that, would run through a Java compiler without a syntax error. Doesn't really matter, but we have all possible programs. Of those, some are, Java programs, some are PHP, whatever. And then we have a set of those programs. It's not that large if that first one was, infinite, but this one is also almost infinite because these are all solutions that are somewhat correct, that has some reliability. At least one, we could invent one test case that succeeds for these. And within this, all of your code that you've ever written that sort of solved the problem is, right? So this is a reduction of the possible programs to those that sort of is in the direction of the problem that we want to solve. And then within those, we have the uncatchable, often correct ones. Those that solve. You cannot invent an input that causes a failure. And that is the golden calf and what we sort of aim. So a test case is a line through this space. And on one side, we have the correct ones, but we also have incorrect ones. And on the other side are all possible programs on this side of it, on the other side, that does not or causes that test case to fail. So with one test case, we're usually cutting away huge amounts of faulty solutions. So one test case is much better than don't having a test case. But as you see on the other side here, we have a lot of space that, or a lot of, somewhat correct solutions, but not fully correct solutions. So one test case is usually not enough for most problems except the third one. So we could have another one on this side. And suddenly we are getting closer and closer onto the correct one. I would say that with testing, it's very hard to close in exactly within the correct space. So that you're, unless you do exhaustive testing where you have so many test cases, you actually test everything. So we might invent test cases. And look at this one. This line is further away from the correct cloud, right? So there, it cuts away. It's a good test case and complements the other, but it also, does not find bugs closer here. So we would like to have close lines. So this line and the dotted line has a different distance to the correct ones. So one test case can be better at finding more bugs than another test case. So I would say those that are test cases that complement each other, they are working good together, they are cooperating, so to speak. And then you can have test cases that, if you have one test case of that type, you don't need another one. So the dotted line, if I added that test case, all of the tests or all of the programs that it sort of would protect us against, we already have another test case. So when you're working with assignment 1, think of, could I really find a bug that I need both test cases in order to find? Or will one test case protect me against both bugs, so to speak? And then you remember also the accuracy thing, or the goal of that. So we could say that if we have a faulty solution or faulty program for each test case, that test case is unique in finding, then we could motivate that test case. So, but if we have a test case or that every bug that it finds, we have another test case that finds, we cannot motivate that. That becomes redundant code, right? Redundant test cases. So we want to have a slim backpack of test cases with us forward, because every line of code, even every line of test code, needs to be maintained. So try to reduce that. Okay, so how many do we need? And we can have different criteria for adequacy. So one criteria could be this: a test T for a program P, PR is considered adequate if for each requirement in R, so we have an array of requirements, there is at least one test case in T that tests the correctness of P with respect to R. So this is sort of mathematical way of expressing it. What we say that, okay, if there is a requirement, we have a test case for that, right? We've already talked about this, so that this could be one. So the x-axis in this graph is the requirement input domain. The y-axis is the output domain. So the input domain now is just one integer or one floating point, and the y-axis or the output is one floating point. It could be like the square root function or something like that, or the sinus function or something like that. But so with one test case, I can find out something about this this function that we don't know if it works properly. But if I add another test case, we see that, oh, these two test cases sort of line up. As soon as I see two samples in a graph, I start to think about a line. So we could sort of assume that every function, if both test cases succeeded, then this line could be the function that we're implementing. The system under test could be that line, right? But it could be any line that goes through these. So this line would probably be fine to have just two test cases because it's a linear function. But this line, would you really trust the implementation of that with only two test cases? I wouldn't. I would like to have another one. So it depends on the complexity of the function that you're testing, how many test cases you want, right? So these adequacy criteria described here, it's not very secure when you're saying that, oh, you only need one requirement or one test case per requirement. Sort of if I'm the customer and I just want to make sure that the developers has developed my web application and that the things that I need to do can be done in that web application, but we should not spend too much time testing that. We sort of trust each other also. Perhaps this kind of adequacy criteria could be used as an acceptance testing. So I just spend 30 minutes going through the test cases just to make sure that they've implemented all the features I've asked about, but I don't look into the details. I'm not creating 10 test cases for failure login, right? I'm just looking at the main success scenario for logging in, perhaps. So depending on the complexity of the program and also the importance of the program, we decide what kind of adequacy criteria we want, right? So another one could be like this. A test T for a program P with the requirement R is considered adequate if each path in P is traversed at least once. So we have a little bit of code to the right. So we have an if statement. If x is bigger than 2, throw new exception. Right? So that is one way of doing it. And if I'm only looking to those two lines, if I throw the exception, I cannot do the other lines. So I'm going from 1 to 2 here, from the 1 line to the 2 line. And then we have a do while loop. So we do, and then we have increase the value of x while x is less than 2. And then that is going to be a loop, right? So if we graph this behavior and we go from, so x is like 1, for instance, then we are up here. We are not going into the if statement. We're going to increase x to 2. And then we're going to step out of this. So and then we're going to return. So 1, 3, 4, 5. I'm going to return 2. And then if x is minus 1, I'm going to go from 1. I'm not throwing any exceptions. I'm going into this one. X becomes 0. X0 is less than 2. X becomes 1. 1 is less than 2. X becomes 2. X is less than 2. And then I go out, right? Which means that 1, 3, 4, 3, 4, 3, 4, 5, or something like that. Perhaps I missed one. So this adequacy is interesting because when we have if statements and when we have loops and stuff like that, we are perhaps not satisfied with this first adequacy criteria because we have a more complex output, or the output depends on if statements and stuff like that. It's no longer just a mathematical formula like the sum method or something like that. So if we have if statement, perhaps it would be good that each path in this graph of the code is traversed at least once. So for this one, I probably want one test case for 1, 2, scenario. So I'm going to call it scenario, but we're actually talking about code here. But this is actually exactly the same thing when we're generating tests from requirements. Okay, so and then we have 1, 3, 4, 5 is another path through this one. But with those two, I don't cover this loop up here. So I have perhaps 1, 3, 4, 3, 4, 5. Yes, so that could probably be a good idea. And yes, this code can be simplified into something else, like return 2. Okay, so it would be interesting if we could, measure that. And this is called coverage. And there are a number of different coverage tools. And coverage builds on something called instrumentation. And just so that you have an idea on how to, how this works, let's imagine that we have this code, and we want to find out if it's covered or not by the test cases. So one way of finding out if this code even run, you've probably done this when you have debugged your own code. You introduce a system out or a console log in order to find out if this code is run or not. So instrumentation works the same way. It runs your code through a specific or a special compiler or a step before the compiler, and it introduces new code. So this is, I call it log, and I call it log method, and I say that, okay, every time this method is called, we make sure that we remember that it was called. And suddenly, when this code was called, I can look in the log, and I can see, yes, this one is covered, and other ones perhaps were not called. And then with this code, I can only find out that this method was started. I cannot find out that we returned something or succeeded. So I cannot differentiate between an exception where connect throws an exception or when it returns something. So in order to do that, we usually, when we instrument, also want to have, another one, another log when we return or before we return, so that we know that, this finished. Now we know that all lines between those two have run. And if we have if statements, perhaps we introduce logs for the if statements also, so that we, we know if we have stepped into an if statement or if we've stepped, into the else part of the if statement. So in the end, we perhaps can produce different kinds of visualizations of this coverage, like this one. So this is an old version of Eclipse and I'm not sure which kind of coverage tool. It doesn't matter. This course is supposed to be tool agnostic, but I want you to explore these tools that are, the tools that are used right now. I know that for Java, I think that there is a tool called Code Cover, and there are several of these. So the write header method, all lines here was run during at least one test, but the close method was not run during a test. The write body was called at least once, and the write file was never called. So we can find that out, and we can, look at the code. Oh, I need to write a test for close and write file and find out. And perhaps for write file, I might need two tests. Perhaps one that steps into the while loop at least once, and one that doesn't, where, the file is empty, so it doesn't go into that, in order to get this path coverage. So we have different kinds of coverage. We can have all different kinds of coverage, really. There are many, many types. So first, let's say that you have divided your application into different components, like a front end, a back end, or an API component, or whatever, or things like that. You can say that, oh, yeah, we have one test case for the back end, or one test case for the front end, or stuff like that. It could also be class. So we have one test case for each class, or one test case for each method, and one test case, or if we have blocks, or we normally use blocks like so. So a block is code that is always run together. So we can say that if number 3 is run, number 4 is always run too. So those, there is no path out of it, this one, except to number 4. So 3 and 4, we can block these and say that, oh, okay, we only need to know if number 3 is run in order to know that number 4 is run also. So we can block all those into separate parts. Just to be clear, instrumentation refers to the technique activity of logging parts of what parts of the code has been run. Yes. So an instrumentation means that we introduce new things into your code in order to measure things on your code, right? So in order to measure dynamic properties of your code, we introduce new statements into it. The interesting thing here is that when we introduce new statements, we're actually changing the behavior of the code, not the actual return values perhaps of the code. But when we introduce new statements, your code is going to take longer to run. It's going to time differently, right? So if we have complex time things, maybe instrumentation doesn't work. There is also something called profiling, which could potentially be used for this. Profiling means that at certain points you stop the program and then you check where are you in the program, and then you continue running it, and then you stop it again. Sometimes profiling builds on instrumentation, but you could do it without. Okay, so blocks could be one way. But in blocks, you cannot really differentiate between 3 and 4, but since they are run at the same time, then that doesn't really matter. So it makes sense to have block coverage. Statement coverage is, I want to talk about line coverage before that, because some of these coverage will also have line coverage. So if we look at this line, right body, this is the socket, and then we call the get output stream, and then we call the write method on its return value, right? And so this actually does several things, this single line. But if we count line coverage, we are only counting that we did this line. So even if we get an exception during the write call or during the get output stream, we cannot differentiate between those runs, so to speak. Line coverage only matters which line, and then statement coverage measures the different things we do in a line, right? So if you have like a variable and then x equals 3 plus 4, the first statement that happens is that 3 is plussed with 4. That becomes 7, and then the second statement that happens is an assignment into x. So we store the value into x. So one line can have many different statements. And then, so those are sort of a pyramid of going deeper and deeper and finer granularity of measurements. And then we have already talked a little bit about the path coverage. One of us make sure that each path is covered. It could be, there are sort of different, I actually don't remember the actual types, or I probably mixed these up, because we have one where we only make sure that each line has been covered once. And then we can have ones that says that, I want to go into 1 to 2, but I want to go from 1, 3, 4, 5, and then I want to have one that says 1, 3, 4, 3, 4, 5, and then I have another one which is 1, 3, 4, 3, 4, 3, 4, 5, and then continue. Since we have a loop, there is an infinite amount of these. I actually don't remember the difference. And then we have decision coverage, which means that we want to make sure that each decision, each if statement. So let's take a look at this code over here. So each if statement has got, or each decision that is made, and this is a decision x bigger than 2, has gone both into the true and into the false. So we have 2 different decisions. But if you have multiple decision in the same if statement. So you can have x is bigger than 2 and x is less than 3 or something like that. I don't have no idea. That becomes stupid. Then you might want to make sure that every possible decision that outcomes from that Boolean expression is traversed. Okay, but since I'm a bit unsure on this and don't know all these by heart, I have provided a link, and you should open this link and read this page. So it's included in the study materials. Here you can, read about coverage and different types of coverage. And I think that I might have missed things up, and I'm happy if you correct me for this. So I just want to see if we have MCDC coverage here somewhere. Yes. Modified condition decision coverage. So this is slightly advanced way of measuring coverage. It says that every point of entry and exit in the program has been invoked at least once, which means that if we have several return statements or several ways of getting into a function, which we don't normally have, but if we have several ways out of the function at least, then we have reached all of those. Every condition in a decision has taken all possible outcomes at least once, which means that the two Booleans have taken all paths. We have come to true or false for all different reasons, actually. Every decision in the program has taken all possible outcomes, at least one, and each condition in a decision has been shown independently affect the decision's outcome. So this is slightly more complex, right? And the reason that they are so thorough here is that we want to use this kind of testing when it's very critical that we are right. We're still within testing realm. We're not doing exhaustive testing, but we are getting sort of closer to exhaustive testing. So this metric is specified for safety critical aviation software, and there is a standard here that you can look at. So look into this a bit. We can discuss it. We can, help you interpret it on Slack, because I don't know it by heart today. Sorry, I don't know everything. So just to recover from the shock of knowing that your teacher doesn't know everything, we take a break, right? So let's have a break up until 14:20. Okay, so welcome back. So we were talking about different types of coverage. And I know that this can be confusing. There are a lot of different things and a lot of different, sort of mathematical expressions of these. But trust me, most of these are pretty simple, like the statement coverage. Do we run each piece of the code at least once, right? So, and that was adequacy criteria, right? So we had we're still talking about different ways of knowing that we did good, right? So from this most simple adequacy criteria to more complex one, which was path coverage and these other types. And so essentially, we as testers need to come up with what is good enough for us. And that depends on complexity, yes. And how important is this? Is this life-threatening? Is it life or death, or is it money, or what? How much money is it? How many bugs can our users tolerate, right? Or so, right? So essentially, we want to do a good job also. We want to be confident, like the first lecture. One of the most important things is that we're confident in the code. We like to work with the code. We start to trust the code. We start to trust the process and stuff like that. So we come up with a criteria and say that, oh, yes, we should have 100% line coverage or 100% loop coverage or whatever. And this might not be as easy as that. So, and I want you during assignment 2 to look at existing projects where other people have done testing, and then you run these, and then you evaluate these. Okay, so let's talk about the problems with using coverage for that. So look at the code to the right. So we have an enum, which is, we can count different parts of an HTTP header. So we've seen the host and content type and content length, and perhaps you've seen HTTP headers before, right? All of these different things. But since we have those things always, if I have a loop like I have down here, I'm just checking, is the string here, is it any of these headers? So I'm going through all the headers and I'm checking a string if it's one of those. If I run a coverage tool on these, I can get 100%. Let's see here, header down here, 100% coverage for the lines or the statements, 100% of the branches, because I'm going into every if statement, out of every if statement. But I only get, see, 66% of the loop coverage. And the reason for that is loop coverage works like this. So if I have a loop, I get loop coverage if I don't enter the loop, if I go through it once, and if I go through it more than once. Then I have, so the 3 different coverage criteria for a loop coverage. And for this particular one, with the HTTP header enum, which always have these, none of those will be removed, right? We can never have an enum with 0 things, right, in it. Then I will, go into it once, go into it many times. I will always go into it, at least once. I will never go into it 0 times. So I cannot get 100% loop coverage. So this means that we cannot reach 100% coverage. So if we decide that 100% coverage is the only thing we're consider adequate for our testing, then we're fooling ourselves, because this cannot be done, at least not in my code. Perhaps you can, solve this somehow. But there are other parts of the code that might be difficult, depending on how good you are at writing your test or your code, so that it's controllable enough so that you can reach each part of the code. So what I found is that error handling code oftentimes are difficult to get coverage for. because perhaps we, because of Java, need to catch some exceptions or throw them further. If we catch an exception, perhaps we, in some private method, try to catch the same exception, whatever, and then suddenly we try to catch it in two different parts, and then if we can never go into the outer one, stuff like that. Some factory code, and with factory I mean classes that calls new. And we've talked about new as problematic for testing before when we're writing unit tests, but this code might also be problematic in getting coverage for. Because sometimes we cannot new objects because stuff is going to happen in the real world when we new object. Because we've written the code so that stuff actually happens when we create an object. And maybe we cannot create those objects during testing because we've written the code that way. Perhaps, missiles are getting launched, or nuclear power plants are going to blow up if you knew the critical code. I don't know. Stuff like that. Before, I think this is doable now, but before you could never start the main method in a unit test, so you couldn't get coverage for that because that was too hard. I think this can be done now. Double checks, yeah, we talked about that. If you have an if statement that checks something and then an if statement within that also checks the same thing, we'll never go into that one. So we can have coverage situations where we actually cannot go into those. So we have hard to test code and we have hard to show coverage for some situation. It could be, when we have resources that are slow, like databases and file systems that we've talked about before, or APIs. Maybe it costs money to call the API. So we don't want to call it during tests because we want to run the test over and over again. We don't want that to cost money. So if it costs $100 to call the API, and some costs that, right? So we can never test that code. Or maybe we do it only once or twice. For some cases, maybe you have special hardware. So I've written a lot of code for Arduinos or other microcontrollers. And I cannot really test the code unless I have the microcontroller and it runs on that. Unless I create a specific sandboxed environment which simulates the hardware. So many of these problems that I talk about can be solved, but writing a simulator for a microcontroller is not like writing a unit test in complexity. It's much more complex. Sometimes we are working with hardware that we only have one of, that we need access to that one and stuff like that. Sometimes we have real input, like on the Arduino, perhaps we need to put current or connect it to a sensor in order to get the kind of input that we would need in order to test this. So not everything is as easy to test as we normally think when we write unit tests. We can have multiple languages in the same file or in the same thing. So if we have, let's say that we have a regular expression inside our Java code or inside our JavaScript code, and we run a coverage tool on our Java code, it doesn't understand regular expression. I'm assuming, maybe someone has created this tool now, but doesn't understand it. And the regular expression itself contains sort of if statements and these different parts of it that can take different paths. So if we're talking about testing all of the program and we actually are having several kinds of languages mixed in each other, perhaps we would need to remove that regular expression and test it separately to make sure that works in every case. Lua is a scripting language, and I've encountered this in a number of different places, like computer games, where we have this computer game and much of the code is C++ or Java code or C# or JavaScript or whatever, but some code is script code, like Lua code. So half of the application is written in another language. suddenly you cannot get a coverage measurement of that because you only have a tool that can only manage one of these. Yeah, so, and sometimes the actual logic of a program is stored as data. I call it data-driven code. It's my expression, I'm assuming it, but sometimes you can, configure an application in a very complex way. Perhaps you're programming it in a graphical editor and you get an XML file out of that, and that is actually code that represents if statements and for loops and stuff like that. So such things, then you have a weird programming language, which is not we don't have a tool for that, really. So even if we have a tool to run the coverage of the interpreter of that JSON or XML file that contains the actual code, we are not running the same thing, right? We're not doing the same thing. And then some complex iterative and recursive functions can be really hard on this also. Maybe they don't end. Maybe there is a simulation going on and they don't end. It's not that easy. So the different cases for that is simulation games in Neuralink. So I'm not saying that these are always impossible. I don't have a solution for this one. That I would call that impossible, right? We cannot get loop coverage if we're looping over an enum that is always. But maybe we could change the coverage tool so that we could, put a little flag over here and say that we ignore the 0 case and still count this as 100%. So nothing is, some things are really impossible, but nothing of this is really impossible. It can always be done. And then we might run into problems like, okay, when I run my tests, I can easily test the public methods. But I have some private methods here, and they are really hard to reach. And perhaps, I need to have if statements or try-catch statements in these private methods. And I cannot really, get into those. I have a problem with controllability. I cannot run the code I want to test. And there are test frameworks which can unlock private methods so that suddenly you get access to them. You could, yourself always make them protected instead of private, and then yourself inherit from the protected class, and then you actually, in the inherited class, you call these methods, the protected methods. And then you can, reach these private methods. Or you say that I'm not going to test the private methods. I'm only going to test it for the public interface. And this is how I do it. And for many cases, there are sort of two, if they're private methods and they are too hard to reach all parts of them, perhaps you're doing too much in this. Some of you have read the book Clean Code. And for instance, I had a piece of code that was working with social security numbers. And social security numbers are 10 to 12 numbers. And then there is, this sign, either a minus sign or a plus sign that divides the 6 numbers from the 4 numbers, right? And some doesn't know that it could be a plus sign, the minus sign in the social security number. And I tried to test this, and I had these parts of the private methods that I could not test. But I realized what I was doing was like, I'm checking that each number here in this part of the string is actually a number between 0 and 9 and not a letter or something like that. And then I could extract another class out of this, which I called numerical string, which had, requirements on it, like, or rules in it, like every position in the numerical string must be a number and not an A or something like that. And suddenly I could have 2 instances of the numerical string, one for the 6 numbers, one for the 4 numbers, and then I had just one character in between that could be a minus and plus. And suddenly entire social security number was easy to test, and numerical string was also easy to test through its public interfaces. Sometimes we talked about mocking, and sometimes some stuff is hard to mock. Actually, I don't know the state of this in Java for particular right now, but you might run into a situation where it says that, oh, you cannot mock this code. At least I've had done it. So we can always wrap and create a test double instead of mocking, I believe. But what we learn from this is that by rewriting our code in other ways, we increase the testability. And the issue is most due to controllability. Sometimes it's observability. And you remember controllability plus observability is testability. Yes. Okay, other problems with considering coverage as the solution to the test adequacy problem, or this, is that some tests may not have asserts in them. So I've looked at a lot of different test suites myself, and I found that, oh, this test doesn't even have an assert. So run the system was a smoke test, and it ran the system. It, did the entire application. And, remember smoke testing, it means that we try to run as large a part of the system as possible. And then we look if it crashes. If it crashes, then we stop and, debug. And there are sometimes, encode asserts or stuff like that we, help in this. The same is for random testing if we're not comparing the output with an expected value. But so smoke tests would just run as large part of it. So if we have one of those smoke tests in our test suite, which we run code coverage on, it means that we're going to have coverage for all the lines of codes that will run when we call system run, or main method in the system, which means that we have coverage, but we never asserted anything, which is sort of reducing the usefulness of the code coverage measurement. So yes, it has run for some input, but we don't know if it gave us the correct output. So we're no longer really testing. So smoke testing is, on the edge of being a useful thing. We smoke test using unit test, but perhaps we don't want to include smoke test in our unit test suites when we are measuring coverage, because we want to make sure that each line of code that is run during the test when we measure coverage actually means something that is, at least for some inputs, correct. Okay, I've also found that I have found a need to write, I call it negative tests and complementary tests. So look at the code in the Slack message here. A constructor should throw when no parameter. So I have a dice class, I have to call it die for some reason. I send it null and not what it's supposed to have, or it's supposed to have a random object. And then I assert fail here afterwards. And you already know that you can, write these tests otherwise now in the latest version of JUnit. So we are testing that it throws an exception if you don't send it correct parameter, right? But in order to test the other path, when it does not throw an exception, I could not really write an assert for that. So I just created a test case where I created a new die, I send it the correct thing, but I don't assert anything. This test is actually not throwing an exception if it's working, right? Or the implementation, if it does not throw an exception, then it's successful. And we know that together with the one that throws the assert or checks that it throws an assert, it's sort of taking two different paths. So it's sort of path coverage. But this one does not have assert. So we need to be able to differentiate between this one that has a little bit of value from the smoke test that sort of reduce the usefulness of coverage. Not every story is simple, as you've heard a couple of times during this one. Okay, so you can have complementary negative tests. Usually, this test is usually you want to call a method on this die class later, right? I want to have a roll the die or whatever, and I want to have some output that I check. And since we always need a correct instance of it, the system under test instance, in order to call a method, that's usually removed later. Okay. Now I have confused you a little bit. Let's confuse you a lot. So we know that it's good to have asserts. It's good to have to run large part of the test when we want to evaluate if the test suite is good enough. But we've learned that smoke tests could exist, and so coverage can be quite useless. And we also know that some code is very complex, and some bugs only occur when we have specific kinds of input, which means that we can have a test case and the code is still wrong. We did see that in one of the first slides with the line, and we only had one test case, and we could, have many different functions for the same one, even if we had a test case. So mutation score is an attempt to see how good is a test case in protecting our implementation from bugs. And the idea is like this: we introduce a lot of bugs into the code and see if those bugs, we call them mutations, are found by our test suite. And we say that if our test suite finds the bugs, then we have a good test suite. So we artificially create defects or mutations and check if our test suite finds them, right? So it sort of decides the test suite's ability to differentiate between the implementation that you have right now that actually could have bugs in it and another muted implementation. Yeah, so we change the system of test, run the test, and see, does it catch the bug or not? There is some problems. I've given some links here. I hope they work still. There is some problem with equivalent implementation. I'm actually going to show it on the next slide. So let's look at this piece of code. Should throw exception as the test. We have an input 5. I call the method that we're testing on the system under test with a 5. And then I assert fail if it doesn't throw an exception. Yes, the okay thing. If it throws an exception, that is okay, right? So then I have this code. This is the original code. If I is above 4, throw exception. That seems to work, right? If I send it to 5 bigger than 4, yes, it's going to throw an exception. We're not going to execute the assert fail. So we are going to catch the exception, and that is fine. The test succeeds for that version. Right now, we're not talking about which implementation is correct. So perhaps this should be bigger or larger than 4. Perhaps that is the correct implementation. Right now, this is the implementation we have with bugs in it. And then we mutate this. So let's change something. So we're just randomly doing stuff to the code. And we're not actually doing, not you and me, the program does. The mutation score program does this. So it takes your code and then it scrambles it a little bit. Let's change the bigger than to less than. So we have a new one. And this is actually a buggy version, right? It's compared to this one. Even if it's larger than and equal to 4 is the correct one, this would be a buggy one. And then let's run this test case again. So we input 5. 5 is not less than 4. So it's not going to throw an exception. We're going to catch this bug. Fine. You see? Good test for that bug. This bug, it's not going to catch. I bigger or equals to 4. So when we send it to 5, it's not going to catch that one. For this input 5, the original implementation and the mutation works the same, right? For this specific test case. So in order to differentiate between this one, I would also need another test case that tests with a 4, right? If I had 2 test cases here, I could kill this bug also, or this mutation also. I think we should ignore that and talk about that for the last slide, because we're getting in. So this last one, let's look at this one. Now we've changed 2 things. This is another mutation. And we changed the larger to larger and equal, but we also changed the number into a 5. So we can have multiple bugs when we mutate, right? But this one, let's throw it a 4 and let's see what happens. Let's assume that we have 2 test cases now. We throw it a 4 and it should not throw an exception, right? 4 is larger or equal. No, it's not. It does not throw. Then we have the test case with the 5 that we have here on the left. 5 or is equal to 5. Yes, so it throws an exception. It works. For any input, this blue one and the original one are equivalent. So actually, we mutated the implementation, but we found another correct implementation, or the similar. So let's look at the definition of mutation score again. And down here, these are called equivalent implementation, which means that when we randomly shake the code a little bit to, change stuff in it, we might end up with code that are actually the same. And we cannot know if this is a buggy version or not. We don't know if this version is buggy or not. So when we calculate the mutation score, which is how many of the mutation did we kill? 1, 2, 3. We killed 1/3 of the mutation, so we get 30% or 33% mutation score here. Which means that actually we should have, if we're, we should have the correct mutation score, it should be 50%. Because this one is not a mutation. It should be counted out. But we cannot really know that. Okay. There is a final, a bit complex version of... So I hope you didn't find these... No, I'm just joking. Some of these coverage tools are pretty, complex, and you need to think about this once or twice, or listen to this lecture a couple of times, and then think about and run the tools in order to find it out. Me and a German researcher had sort of the same idea, and we thought about, what if, we have this coverage measurement and they all suck. They all have problems with them. So let's try to solve this. And my idea was that, and actually this David Schuler's idea also, but he was actually a year or 2 before me and think about this. And I never learned that until I was done with it. Then I searched for papers on it, and I found his. Whatever. So my idea was like this. If you look at do calculate, we have some x variable, and we have some calculations with x, and then we return x. And then we have a test for this, which calls do calculate, sets a value for y up here, and then checks that the return value, the x thing, is 4. Doesn't matter if it's not or no. But if you look at this code, this is affecting the return value. This piece of the code is also affecting the return value. But the printf statement, which is a system out print line, is essentially, is not changing the value of the return value. So first line, these lines, and the return line is asserted, so to speak, is checked by the assert, but the print is not. Doesn't matter, right? So there are ways of doing this. It's called dynamic slicing and a bit of magic, right? Yeah, and the idea is that we only count lines of code as covered if they also affected the outcome of an assert. A bit complex, and it was not easy to implement, trust me. But I did that, but David had done it before. So I think there is his paper here, if I remember his name correctly. Who knows? And maybe the link is down. I have no idea. Yes, David Schuler, yeah. And yeah, it's a quite interesting thing, but a number of years ago. I think they have continued to work on that, but I stopped when I learned that someone else had already done it. There are things that we cannot assert about, and things that did not happen, for instance. So, and then I also learned that a number of paths, like through file databases or other languages, cannot be asserted about either. So this is also not a silver bullet for finding out if a test suite is good or not. And then I compared statement coverage, mutation score, and checked coverage, and put the same thing in the graph and created a number of test cases and stuff like that. So, and what I've learned from this is essentially the top one, I think, is like statement coverage, and the red one is when the program crashes because of a bug, and then the blue ones are exceptions are thrown or something like that, and the green ones are mutation score. I actually don't remember. Doesn't matter. But what we see here is that each X position in this graph is a statement in the code. What we see is that these overlap with each other. So we could, run multiple tools and find out that, oh, this line of code is covered, or this kind of line of code is not covered, and stuff like that. The green one is less sort of not always covered by the other ones. So this checked coverage thing is a good idea to have. But today, I don't know how the tool works for this, if it's usable or not. But at that time, when I wrote my tool, it was not usable. So if it's not usable, then it's not accessible for developers. So what is accessible? It's the coverage tools, really. You could also run the mutation score tools, perhaps if you're really worried about these things. And I would say for assignment 2, it would be interesting if you run a mutation tool. I think these tools have evolved since I used them. So try it out. Learn about this. What can you learn from this? But when you look at assignment 2 and perhaps assignment 1 also, and you count lines of code covered, or loop coverage and all of this, have all these problems with you. And when you interpret the result, don't just say that, oh, we got 90% coverage, it's really good, or 90% or 100% coverage, it's perfect, it's correct, right? Because it's not. We actually right now don't have any really good way of accurately for every case knowing the quality of a test suite. I'm sorry about that, but yes. Finally, assignment 1, part 2 is about test-driven development. And I want you to take a look at the pre-recorded lectures on where I program some test-driven development. I'm actually doing it in PHP. Doesn't matter, because it's the process and not the tools that I'm using that matters. So if you read the Kent Beck book on test-driven development, he's going to say that insufficient coverage is a sign of badly designed tests. And that if you follow the test-driven development methodology, you're going to get good design tests, and then you're going to get good coverage, but that the coverage actually doesn't mean so much as following the process, because the test suite that you're going to get is going to be a good test suite. So I encourage everyone to work with TDD. And if you follow this and, stay true to it, you will get really good at writing unit tests, and you will also get really good at writing unit test suites that are valuable. That, at least, is my experience from doing it myself a couple of times, and also experience with multiple years of students doing this assignment. So the part 2 deadline I have not set yet. So my idea is that depends on really on how many people wants to do it. because we want to have oral examination for that. I want to talk to all the students that does this. So the examination might be, spread out over several weeks. So I would say that since I want the assignment 2 to be before Christmas, so assignment 1 is now on Friday, right? So assignment 2 should be before Christmas, 21st of that. Assignment 1, part 2 is, for higher grade. So we assume the students that go for this also can work harder or, do more things. So I think 2 weeks is the tops of assignment 2. But this, you need to work on this. And you should probably have already started with it. Okay, thank you very much for this lecture. Thank you for listening. Maybe you need to read and, listen to this once again when you've read different sources. Thank you very much.